AP Statistics students, we are starting this next section. The unit we are in is looking at our data, specifically our quantitative data, and then how we model those distributions. In the last section, we talked about describing a location. In this section, we're going to be talking about density curves and normal distributions. By the end of this section, you should be able to accomplish these learning targets. This first video is going to focus on the first two of the learning targets about density curves. So it shouldn't be too long. Now, back in the first unit, in the first chapter, we developed kind of a kit of graphical and numerical tools for describing distributions. And now we're going to add a new step to the strategy. So here's how we would explore that quantitative data in 4 steps, right? So we always wanted to make sure we were plotting our data, right? You made some kind of graph, like a dot plot or a stem plot. We looked for the overall pattern, okay? And we want to look for any striking departures, such as outliers. And then finally, we calculated the numerical summary for center as well as for our variability, right? To describe our center and our variability. Now here's our new step. If there's a large quantity of data in a regular pattern, it can be described with something called a density curve. Okay, so when there's an overall pattern, you use a simplified model called a density curve. Now let's talk about this density curve. A density curve models the distribution of a quantitative variable with a curve that has a couple things true about it. It is always either on or above the horizontal axis, so it does not go below it. And it always has an area of exactly 1 underneath of the curve. Okay? The area under the curve and above any interval of values on the horizontal axis is going to estimate the proportion, or the percentage, of all observations that fall in that interval. So this density curve describes an overall pattern of a distribution. So here is an example. You can see this is a dot plot that's showing however long a journey took in minutes after many iterations of it. So maybe this was someone's commute or something. And you can see how it's pretty uniform. So the overall pattern, here's the data. The overall pattern of this dot plot is the amount of time it's taken Selena to get to the bookstore by train each day for the last 1,000 days. So when you have a lot of data like this, you can give this more fluid distribution, a nicer looking graph. This is called a uniform distribution. You can see here how it's pretty straight across, right? It's not bell-shaped, it's not skewed right, skewed left. This is pretty much uniform. We see that it ranges from 2 to 5, and that the height here is 1/3. Now, why would the height be 1/3? Well, the distance between 2 and 5 is 3, and in order for the area underneath to be 1, you need to have a height of 1/3 times by 1. It gets more complicated in graphs that are more curved, okay? So in this histogram, we can see the overall pattern of scores of 974 7th graders for a particular test. Now, the curve doesn't exactly fit it, right? You'll notice some parts are under it, some parts are over it, but this is a very good kind of estimate of the overall pattern. So this is called the density curve. Let's talk about the mean and the median of a density curve. Because it's a generalization, the density curve has a mean of mu, right? That's that Greek letter mu, which is the population mean, and a standard deviation of sigma, that lowercase sigma in the Greek, which stands for the population standard deviation. Think of the mean as the balance point of a density curve, right? If this curve was made of solid material, like wood or something, where could you put it? So it's kind of like, I think it's called the fulcrum. Where would it be so that it would balance? So not here, tips down, not here, tips this way. Right here is a balancing point. Now the median of your density curve is going to be the place where the equal areas point, right? It's the point that divides the area under the curve in half. So not necessarily at the peak, especially if it's not a symmetric curve. The median might not be right there. So if it is a symmetric density curve, the mean and the median are going to be equal. But in the skewed one, the mean gets pulled towards the tail. Okay. You can see that in this example here I've got a symmetric one where they're the same, but in this one we have the median that's been pulled and the mean is pulled even more. Let's look at an example. We want to know, why is this a legitimate density curve? About what proportions of the observations lie between 7 and 8? And then which would you say is greater in this distribution, mean or median, and why? Take a minute, pause this video, literally press pause, and try and answer these questions on your own. And when you unpause, you'll see the answers. The reasons this is a legitimate density curve: the area under the curve is 1. It's printed there for us. And we can see that the curve either lies on or above this horizontal axis. The proportion between 7 and 8 is 0.12. That can be seen as the area. Those are going to be synonymous here. The area under the curve represents the proportion in that particular interval. And then which is going to be greater? Well, the median will be greater because the density curve is skewed left, so the mean is pulled to that tail. If I had to estimate, I'd say that this line here would represent the median, and then this line to the left of it would represent the mean. So, reiterating a little bit here, the density curve, like we said, is an idealized description of a density, or description of data. We distinguish between the mean and the standard deviation of the density curve computed from the observed actual values, always using that notation of mu for the Greek letter mu, and that's our population, and then the standard deviation is our sigma. Now, just make sure you're aware that not all density curves are going to necessarily look curvy, right? This is the uniform distribution from before. This also represents a density curve, okay? The area under the curve, and I use that word loosely here, will always be 1. So we talked here about this curve having a height of 1/3 to make sure the area underneath was 1. If you dropped this down and kind of imagine it being like a right triangle, you would have, okay, well, if this is 4, area under of a triangle is 1/2 of the base times the height. So you notice the height is a half, because half of 4 is 2, and 2 times a half is 1. So the area under this quote-unquote curve is still 1. If you look in your textbook, you'll see more examples about that, and then do some practice problems involving these density curves. In our next video, we'll talk about a special type of distribution, a special type of density curve called a normal distribution.